So, dear students, in this video, I'll be discussing non-inverting operational amplifier. Now, we have already talked about an ideal operational amplifier, and we have talked about uh, the open loop gain of an amplifier. Now here we have an operational amplifier, and we will subject the output, a part of output of operational amplifier, back into the into the input. Now what we have to discuss here is the non-inverting operational amplifier. So if I draw an operational amplifier, and we understand it has two inputs, one is positive, another is negative, and here we have the output, V out. Okay, now if I choose the part of this output with a resistance known as feedback resistance back to the terminal, and since it's a non-inverting operational amplifier, the signal that will be input in this case would be to the positive terminal of this operational amplifier. So here we will be using a signal uh, to the to the non-inverting terminal of operational amplifier, and this part will be grounded, and this is the feedback resistance. Let us symbolize it as RF, and okay, there will be a current. Let us assume that this current is IF, and here we have a junction, and we can think of some part of current in this direction, some part of current in this direction. So let us assume this is I, and this is I1, and here we will use a resistance, and that resistance will be Ri. So this is the circuit diagram for a non-inverting operational amplifier, and things are quite simple here, and we better understand that we have used a feedback, and obviously the feedback is connected to one of the inputs of this operational amplifier, and we assume that the current passing through this feedback resistance is IF, and we divide this current into two parts, I and I1. Now to analyze this circuit and to have an expression for the closed loop gain, because here we have a situation of closed operational amplifier, because a part of its output is subjected back to the input of the operational amplifier. Now, to start with, if I have to make use of Kirchhoff's current law, so for this situation, for this junction, I can say this IF is I plus I1. So this should be the case. So we are using KCL here. Okay. Now let me assume that the voltage of the signal is Vs, and here we have a voltage equal to V2. Here we have a voltage V1, and uh, and and we have the current here. Okay, then we have the resistance here, and this terminal is grounded, and this terminal is subjected to an input signal. Now here we have to make use of the concept uh, of uh, of virtual short, and then later on virtual ground. Now we can see here, we understand that the input impedance of an operational amplifier, I mean ideal operational amplifier, is infinite. Now if input is infinite and we are having a current I1, okay, so if I draw the dotted lines here, to realize that the input resistance is extremely large, then according to Ohm's law, the current flowing through this resistance will be equal to zero, right? So in that case, so for an ideal operational amplifier, for ideal operational amplifier, what we have infinite, we have infinite input impedance, right? So if the input impedance is infinite, then we can presumably say that this I1 is equal to zero. So this equation will reduce down to IF equals I, right? That's the case. I think that's quite understandable. Okay, now let's proceed from here. Now let's look for the voltages that are in, because IF will be the current, and I want to write this IF in terms of resistance and in terms of voltage. Now for IF, what we have so for IF we have V out by what we have V out by RF, right? This is for IF, and for I, here is I, okay? So for I, we have the potential here V2, that is V2 by RI. All right, this is the case. I think this is clear from up to this point, that we have written down this equation in terms of voltage and resistance. So now coming back to this diagram, we have a situation here, and what situation we have? We have already talked about the current that's flowing through these two ports, -1 and +1. Since the resistance is infinite, the current passing through this is zero. So what we can presume here under this situation is that if V1 is the potential is the potential at this point, and V2 is the potential at this point, right? And then we have Vs, the potential at this point, right? Now, since there is no flow of current, what we can assume here is that the signal voltage must be equal to V1, and this V1 must have the same potential as that of V2. And this condition is known as virtual ground. This has been explained already in the previous video. So that's the case here. So what is the case here? Here the case is that this Vs is equal to V1 is equal to V2. So the reasons for this is virtual ground. Right? So we can use here, instead of V2, we can use Vs. So V out by Rf is equal to Vs by Ri. So I can write down the output voltage for this inverting, non-inverting amplifier as Vs times Rf by Ri. So till now, the situation is like this. Is it okay? Now, if we go back, back to the original course here, and what we have done in the previous case is that we have V out. Okay, what we have V out minus V2. Okay, we have boiled down that. Okay, we have not written that equation first. I mean, here, if we go back here, in actual situation, this is V out minus V2. So this is V out minus V2. Oh, sorry. This is V out minus V2 divide by RF. I have committed a mistake, I think. This is equal to V2. Now, now V2 is okay, nothing wrong with V2. This is V2 by Ri. Okay, so for I, it is simply V2 by I. Okay, so here is a little bit of correction that I have to do. Here it is V out minus V2. So if that's the case, here it will be V out minus Vs. All right. Okay, this was the mistake. I have committed the mistake here. Now I have rectified it. So if this is the case, I have to modify it. So what will be the result? This will be equal to V out by Rf minus Vs by Rf is equal to Vs by Ri, right? So V out by Rf will be equal to Vs times 1 by Rf plus 1 by Ri. Okay, so now we can get the accurate equation that we are interested in. That's the output voltage for inverting operational amplifier. That is equal to Vs times Rf by Rf plus Rf by Ri. So the final equation that we will get for the output voltage will be Vs times 1 plus Rf by Ri. So the things are quite clear here, that the output voltage that we will receive from the receiving end will be signal voltage times 1 plus Rf by